Dear students, today's topic is special theory of relativity and breakdown of classical physics. The topic code is EMREL-S2. The Einstein in 1905 proposed the fundamental postulates of special theory of relativity. The postulates can be stated as follows. The first postulate states that it is physically impossible to detect the uniform motion of a frame of reference from observation made entirely within that frame. Means if you are sitting in a certain frame of reference and that frame of reference is moving with a uniform velocity, that is, it is the non-accelerated or inertial frame, then this postulate says that it is impossible to detect an observer which is sitting inside that frame of reference the motion to detect the motion of that frame of reference. The postulate is quite clear in itself. We can explain it further to emphasize its meaning. It means that any experiment gives precisely the same result whether it is performed in reference frame 1 or in reference frame 2, or whether it is performed in a stationary or in a moving vehicle, as long as there is no acceleration. If we are given some physical law like the Newton's second law of motion, let's say some force F1 is equal to m1a, makes some object of mass m1 and moves with the acceleration a1. The Newton's second law of motion, which is valid in reference frame 1, there exists an identical law F2 is equal to m2a, which is valid in reference frame 2. In fact, there must exist a transformation that render all the laws of nature are identical in reference frame 1 and reference frame 2. The second postulate of the special theory of relativity is that the speed of light is independent of sources and is constant in all frame of references. In all frames or frame of references. So these are the two postulates. Now we move on to the breakdown of the classical laws. Why there was a need of the special theory of relativity. First, we take the example: the particle velocities never exceed c. This is the universal. Obviously, the speed of light is a universal constant. So we take a look in the classical way. The usual expression for the kinetic energy is equal to half mv square. In classical mechanics, the mass, classical mechanics, of mass m, an object of mass m, a mass m of an object moving with a velocity v cannot be correct in relativistic frame of reference, as the velocity of the particle does not increase indefinitely as its energy increases. Instead, velocity approaches asymptotically the velocity of the light, which is c is equal to 3 into 10 to the power 8 meter per second. So the law does not hold, or that relation does not hold in the relativistic frame of reference, that if we have we put the speed of the light as a 3 into 10 to the power 8 meter per second, so it will make it the energy of the object and almost infinite. So that is not possible for having infinite energy of a particle. Similarly, example 2, the addition of velocities in a classical vector addition, which is applied in Galilean frame of reference, that is the classical way of where the motion are not of the relativistic level, not of that high speed, close to the speed of light. So that is if a passenger walks with a velocity v toward the front of a train, that itself moved forward towards the passenger with a velocity capital V, then his velocity with respect to the ground is simply the vector sum v plus v. But this simple addition of velocity is found to be incorrect at relativistic velocities, that is near the speed of light. Rather, resulting velocity found always smaller than the v plus v and never exceeds c. So suppose this some object is moving or inside that compartment or the frame of reference, some light is traveling, and along with that this compartment is also moving with certain velocity v. So altogether what we do, we add these two velocities, so which will make the velocity of that total object moving towards that observer will be greater than c, which is not correct. Rather, the velocity never exceeds c, rather it is smaller than the that c. The third example, we take the time dilation. The Galilean assumes that the time t as measured in the moving train is the same as that measured on the ground. Now, if the observers have identical synchronized clocks, this also found experimentally incorrect. At relativistic velocities, the time is dilated. So the Galilean transformation failed to explain the electromagnetic fields phenomena in the propagation of electromagnetic waves. So these were this introduction to the special theory of relativity and the causes or the reasons for the breakdown of the classical physics. We reach with this to the end of the topic. Thank you.